Right now, a faint red star circles through the darkness, just 4.24 light-years away. It is close enough that its light left during your last birthday, yet distant enough that no spacecraft humanity has ever built could reach it within your lifetime. We call it Proxima Centauri, the smallest member of a triple star system. Around that star, hidden in a halo of cosmic radiation and magnetic storms, lies a world that has captured our imagination more than any other. Proxima b. Tonight, we'll explore what this neighboring world truly is, what it might have been, what it could become, and why Proxima b may hold the most unsettling lesson for the future of planets like our own. If you enjoy cosmic journeys like this, please like and subscribe and tell us where in the world you are listening from. Let's begin. Proxima b orbits our closest stellar neighbour, a red dwarf only 14% the size of the Sun. Its average distance from Earth is so small that, on a galactic map, it would look like we are brushing shoulders. Yet those 4.24 light-years separate us by more than 25 trillion miles, far beyond the reach of any probe we've launched. That gap reveals an uncomfortable truth about interstellar space. Proximity does not equal accessibility. Even the fastest object humanity has ever built, the Parker Solar Probe, would take tens of thousands of years to reach this world. The nearest planet beyond our solar system is close enough to imagine, but distant enough to make imagination feel useless. We live in a civilization that crosses oceans in hours and orbits Earth in minutes. But the gulf between us and Proxima b is a wall of time. Travel is not a journey. It is a legacy. Any mission we send there would be completed by people not yet born, or perhaps by machines that no longer recognize us. Astronomers first detected Proxima b in 2016 using radial velocity methods. They did not glimpse it directly. Instead, they watched its star wobble. Proxima Centauri is so light that even a modest planet can tug it off balance. That tiny gravitational dance, measured through subtle shifts in the star's spectrum, announced Proxima b's presence. It weighs a minimum of about 1.3 Earth masses, heavy enough to be rocky rather than gaseous. We do not know its mountains or oceans, its storms or silence. We only know that its gravity leaves fingerprints on the star it orbits. This is how alien worlds are discovered, not by eyes, but by inference. We read ripples in starlight and interpret the invisible. When Proxima b was confirmed, the world reacted not with collective fear or skepticism, but with a quiet surge of possibility. For the first time, the closest exoplanet was not a gas giant, not a frozen dwarf, but something Earth-sized. Something that could, at least in theory, hold liquid water. That alone made it historic. Proxima Centauri is a red dwarf, a category of star that burns slowly, dimly, and with astonishing patience. While our Sun will live for about 10 billion years, Proxima will endure for trillions. Its light is weak, but its life is long. If life ever formed near such stars, it would have ages to evolve. The challenge is surviving the violence of youth. Red dwarfs flare aggressively when young, unleashing radiation storms capable of stripping atmospheres and sterilizing surfaces. Proxima b orbits close, 20 times closer to its star than Earth is to the Sun. The proximity grants warmth, but also punishment. Imagine a civilization around Proxima b. Not a mythic advanced species, just a simple biosphere. Microbes tucked inside soil, algae beneath oceans, organisms that know sunlight, not as brilliant gold, but as cold red ember. It would pulse under the moods of an unpredictable star. Growth and retreat, chemical evolution, survival under constant bombardment. If life exists there, it would not resemble Earth's. It would be resilient in ways we barely understand. We call Proxima b nearby, yet we observe it through instruments positioned on a tiny planet orbiting a yellow star. Every fact we know comes from light stretched across years of vacuum. If we ever set foot there, humanity would cross that void not as explorers of new land, but as visitors in an ancient neighborhood where stars burn slowly and planets learn endurance through fire. Proxima b likely does not spin the way Earth does. Gravity has twisted it into tidal lock, one half forever staring at its star, the other frozen in endless night. Day and night are not cycles here. They are hemispheres. Imagine standing at the center of the day side. The sun would never move. It would not rise or set. It would hang in the sky like a red wound, fixed in place, pouring radiation downward with no relief. Shadows would not sweep across the land. They would be permanent, carved into terrain like scars. Every plant, every rock, every structure would forever face the same direction. The concept of morning or afternoon collapses. Weather becomes a matter of geography, not time. Tidal locking happens when a planet orbits so close to its star that gravitational forces gradually slow its rotation until it matches its orbital period. Earth's moon is an example. Only one face ever looks toward us. On Proxima b, this effect is magnified by its tight 11.2-day orbit. Over geologic timescales, friction in the planet's mantle and tidal forces drain rotational energy until the world stops turning. At that point, the star claims one half forever. The other becomes a frozen shadow. The day side would be blistering, illuminated constantly by radiation the planet cannot escape from. Rocks would heat until they reached equilibrium with the crimson sky. Winds would rise from hot to cold, generating vicious atmospheric circulation. Superstorms could dominate the twilight belt, the narrow region between day and night, where rising air from the bright hemisphere slams into frigid gases from the dark one. These winds would not migrate beyond seasons. They would be the climate. The night side is another universe entirely. Without sunlight, temperatures could plunge to values far below terrestrial polar regions. Oceans, if they exist, may freeze into continent-wide plates of ice. With no source of warmth, the ground would become brittle, silent, and ancient. There would be no sunsets, just endless darkness broken only by the faint glow of the stars or the red flicker from Proxima's distant flares reflecting off the atmosphere. The cold might be so deep that even gases like nitrogen could condense as frost. But tidal locking is not an instant death sentence for habitability. Atmospheric models suggest that if Proxima b retained a thick enough atmosphere, perhaps comparable to Venus's, heat could circulate from the sunlit hemisphere to the dark one. Pressure systems could carry warmth across the world, preventing catastrophic freeze-out. In that case, the night side might not be a dead ice desert. It could be a cold, stable realm where life finds shelter from radiation. There is also the possibility of oceans. Water distributes heat more effectively than rock. If oceans once formed here and remained deep enough, currents could move energy from bright to dark hemispheres. Beneath the twilight belt, waves could churn endlessly against coastal cliffs, carving a shoreline that never sees sunset and never sees dawn. Human explorers landing on Proxima b would experience a world defined not by time but by distance. Travel a few hundred kilometers, and you move from scorching daylight to a frozen landscape illuminated only by stars. There is no rotation to soften these extremes. There is only the star on one side and the infinite night on the other. Standing on the day side of Proxima b, the sky would never grow bright blue. Instead, the star would loom large, a dim red disk bathing the land in copper light like perpetual sunset. Shadows stretch endlessly, as if time itself forgot to move. The sunlight here is not gentle golden warmth like we know on Earth. It is infrared rich, stripped of the blue wavelengths that paint our skies. The atmosphere, if it still exists, cannot scatter the light enough to create color. Everything would appear muted and heavy, as though each surface is dusted in rust. Rocks bear a dull sheen. Plants, if any, absorb the light greedily, and water takes on the deep, oily darkness of a planet lit by fire instead of flame. Astronomers call Proxima Centauri an M-dwarf. These stars burn cooler and dimmer than our Sun, emitting most of their energy as red and near-infrared radiation. Their light is constant even when they are calm. Unlike Earth's days, defined by brightness that lifts and fades, Proxima B's dayside is a fixed lesson in endurance. There is no dawn to gently warm the landscape. There is no afternoon peak, no evening relief. Only one eternal condition: the red sun, unmoving, pouring low-energy heat onto the world. Under such light, entire ecosystems, if they exist, would evolve differently. Photosynthesis here would need to rely on pigments capable of absorbing wavelengths that Earth's plants ignore. Instead of the green chlorophyll familiar to us, life may turn dark, purple, maroon, or nearly black to capture every precious photon. On Earth, twilight is a transitional moment. On Proxima b, twilight is the baseline. What we treat as a passing mood, this planet treats as the default state of existence. A constant star means a constant ceiling of heat. Rocks continuously warm. The ground never experiences nightfall to cool. Without rotation, there is no daily reset. Over years and centuries, the surface reaches an equilibrium dictated by atmosphere, composition, and stellar intensity. Dust storms could swirl endlessly, stirred by the vertical temperature gradients between burning plains and high-altitude cold. Everything takes on a slow, grinding permanence, like a planet stuck halfway between dawn and dusk. The sky itself would be unsettling. Even during flares, the star may not seem brighter, just angrier. Proxima Centauri regularly emits high-energy bursts, saturating its surroundings with radiation. From the ground, these flares could paint the upper atmosphere with brief ribbons of harsh red or violet. Not auroras like Earth's polar curtains, but sudden pulses like electric scars flashing overhead. Each storm would remind colonists or organisms that the star above is not a benevolent sun. It is a quiet embosphere fueled by chaos. If you walk across the terrain, you never see your shadow shorten. It stretches, unwavering, fixed like an anchor behind you. On Earth, shadows offer a sense of time passing, the planet's rotation measured softly on pavement and sand. On Proxima b, shadows tell you nothing. They only remind you that the star never moves. The emotional weight of such a sky would be profound. Humans are creatures of cycles, mornings that promise, nights that end. On this world, there is no such rhythm. Time becomes geography. The sun's position is not a clock, but a direction on a compass. Travelers would not ask when the sun sets. They would ask where the cold begins. Under a red sun that never rests, life must adapt or accept extinction. Proxima Centauri erupts frequently. Solar flares can blast X-rays hundreds of times stronger than those from our sun. Any atmosphere on Proxima b faces these explosive barrages like a fragile shield battered by cosmic hail. Red dwarfs are small, but their tempers are enormous. Unlike our sun, which maintains a fairly predictable rhythm, Proxima is volatile. Magnetic fields twist and snap across its surface, releasing energy in sudden bursts. Astronomers have recorded flares so powerful that, for minutes at a time, the star brightened by an entire order of magnitude. Imagine standing beneath a dim red lamp and, without warning, being struck by a lightning strike powerful enough to tear the lamp apart. That is daily weather around Proxima Centauri. These eruptions are nothing like Earth's solar storms. When our sun flares, It releases charged particles that can disrupt satellites and power grids. But our thick atmosphere and magnetic field diffuse much of the danger. On Proxima b, the storms are constant, aggressive, and often unpredictable. They can strip atmospheric gases away molecule by molecule. Hydrogen, the building block of oceans, is the first to flee. It rises, ionizes, and disappears into space like steam boiling off a pot left on a burner that never cools. Radiation is not just a single burst. It comes in layers: ultraviolet, X-rays, and high-energy protons. The ultraviolet burns the atmosphere, the X-rays punch through it, and the protons follow, smashing the remnants apart. These waves arrive like a coordinated assault, each phase making the next more lethal. The star may look small and faint, but its storms are not gentle, and they are not rare. They are a defining feature of Proxima's nature. Because Proxima b orbits so close, it cannot escape the blast zone. It hugs its star the way Mercury hugs ours, but Mercury at least gets periods of calm. Every flare injects energy into the upper atmosphere, accelerating particles outward. Over millions of years, erosion becomes catastrophic. Oceans evaporate, air molecules lift like dust, the sky becomes thin, then transparent. Scientists studying flaring red dwarfs worry about more than lost air. They worry about chemistry. A planet bathed in X-rays might see oxygen split into unstable radicals. Nitrogen could convert into compounds that destroy ozone. The atmosphere becomes biologically hostile. Even if life begins, it must survive not just one disaster, but millions of them. But this is not the full story. Some models suggest a thick, pressure-dense atmosphere could resist the tearing. Think of Venus: toxic, dense, unwelcoming, but resilient. A blanket of gases dozens of times thicker than Earth's could absorb the flares, distributing their heat and softening the worst effects. Life would not thrive on the surface. It would migrate into oceans, caves, or even microscopic habitats beneath stone. Human explorers would need shielding. Surface settlements would not resemble Earth's cities. They would be bunkers carved into bedrock, sealed behind radiation shutters that close every time the star lashes out. Spacesuits would not protect the wearer from a bad flare. Emergency shelters would be mandatory. Interstellar colonization is not a dream of open skies here. It is a fight against a star that never learned restraint. Proxima Centauri promises longevity, trillions of years of possible light. But longevity does not mean safety. It means a slow-burning furnace interrupted by violent tempests. For Proxima b, those storms could be the difference between a living world and a silent one. Some models suggest Proxima b once had oceans and a thick envelope of gases. Others predict that the star's radiation has peeled its atmosphere away, leaving desert rock exposed directly to vacuum. Both futures are possible. Atmospheres are not guaranteed. They are fragile, shifting, and easily undone. Earth's air seems permanent because we live within it. But its existence depends on magnetic shielding, volcanic replenishment, and a comfortable distance from the sun. Remove any one of those ingredients, and our skies could thin, collapse, or burn away. The planet sits so close to its star that atmospheric molecules are constantly bombarded by radiation. The lighter ones escape into space, the heavier ones degrade into unstable fragments. What remains, over time, becomes a stripped shell rather than a breathable shield. Scientists attempt to predict the planet's past by modeling its early conditions. One scenario paints Proxima b as Earth-like. Blue oceans, clouds drifting along a rotating world, water cycling between sea and sky. Under this model, the planet formed with ample hydrogen and carbon dioxide. Volcanic eruptions helped thicken its atmosphere, and the early radiation was not yet strong enough to vaporize oceans. For millions of years, conditions might have been forgiving. Warm, sunlit days on the facing hemisphere, frozen darkness on the far side, but stable enough for liquid water to exist. Then Proxima Centauri aged into its flare phase. Red dwarfs do not settle quietly into adulthood. They erupt. X-rays penetrated deep into the upper atmosphere. Charged particles battered it from above like hailstones made of energy. Ionized gases drifted outward and never returned. Minor atmospheric loss accelerated into catastrophic evaporation. In this version of the planet's story, oceans boiled away until they were gone. The surface transformed into cracked lithosphere. Its seas vanished into the void. The alternative scenario is harsher from the beginning. In this model, Proxima b never kept its atmosphere long enough to nurture water. The star's radiation during its youth, far stronger than it is today, may have stripped volatile compounds before oceans could form. Hydrogen, the key element in water, is the easiest to lose. Once it escapes, oxygen remains behind, chemically reactive and dangerous. It forms peroxides, bleaches minerals, and sterilizes surfaces. What looks like air becomes poison. The planet may have been hostile from the moment it cooled. There is a third possibility, quieter and more alien. Perhaps a thick atmosphere endured, but not a pleasant one. Imagine something more like Venus. Dense, acidic, and crushing. A blanket of gases so heavy that particles from Proxima's storms never reach the surface. The day side simmers in endless greenhouse effect, and the night side freezes under its own weight. A world divided not by rotation, but by pressure. Oceanic clouds might exist high above, but rain never touches the ground. Even if an atmosphere remains, it would not be calm. Winds would flow constantly from hot hemisphere to cold, racing around the twilight zone in planetary-scale jet streams. Dust and aerosols would accumulate on the daylit face, forming vast sheets that glow dimly under the red sun. Every gust would be a reminder. The air is not your ally. It is an arena where radiation, heat, and chemistry battle for dominance. Proxima b may be a barren stone wrapped in void, or it may carry a suffocating cloak that hides oceans locked beneath ice. We have only the signatures of its gravity on its star, the faint fingerprints of its existence in starlight. The truth is still hidden on the far side of 4.24 light-years. Waiting between the scorched day and frozen night may exist a narrow band of dusk, the terminator zone. Here temperatures could allow liquid water. Life, if it exists, might cling to that dim line where dawn and dusk never end. On Proxima b, this region would be more than a line on a map. It would be an environment shaped by delicate balance, where incoming radiation from the star is nearly equal to the heat lost into the abyss of the night side. The temperature gradient here could remain stable enough for rivers, lakes, and seasonal clouds. Unlike Earth, where climate is sculpted by rotation and seasons, the terminator zone is defined by proximity. Take one step toward the star, and you walk into scorching heat. Take one step toward night, and frost stretches beneath your feet. To survive here is to occupy a razor edge between extremes. Winds would dominate everything. Atmospheric circulation would constantly sweep heat from the star-facing hemisphere into the cold. Currents could coil around the planet like a ring, moving west to east in a permanent jet stream. Air would rise from the bright side, expand, cool, and descend into darkness, only to be pulled back again. These winds might howl relentlessly at ground level, stripping loose dust and shaping the land into endless dunes. The sound of the twilight belt would not be silence, it would be breath, the planet exhaling heat across its skin. Rain, if it forms, would fall differently here. Clouds born on the daylit side would creep toward night, condensing as they enter cooler regions. They might break open over a landscape of dark stone and violet skies, soaking the soil before evaporating again under the slow seep of heat from the bright hemisphere. If oceans exist, their shorelines would likely trace this belt in long, crescent arcs. Waves would churn endlessly, driven by the winds rather than tides. The sea would not be a gentle reservoir. It would be a conveyor of energy. If organisms evolved here, they would adapt not to cycles, but to gradients. On Earth, plants track the sun. Animals migrate with the seasons. On Proxima b, life may simply drift sideways, toward or away from the star, as conditions change. Microbial mats could cling to rocks warmed just enough to prevent ice, shaded just enough to prevent desiccation. Larger life, if it exists, might burrow or root itself into the terrain to avoid the violent winds. Camouflage becomes irrelevant. Survival depends on temperature tolerance and radiation shielding. Imagine a human settlement built here. It would not resemble a spreading city. It would stretch in a long ribbon across the planet, a chain of habitats following the only livable geography. Colonists would measure distance not in kilometers, but in degrees of light. A few meters toward daylight, and equipment overheats. A few meters toward darkness, and machinery freezes. Architecture might lean underground, carved into stone to hide from flares and maintain constant temperature. Even power systems would be directional. Solar collectors facing the red star, heat exchangers facing the night. Above all, the twilight belt is fragile. A shift in atmosphere, a flare more violent than usual, or a change in orbital eccentricity could collapse this zone entirely. The narrow region of liquid water could evaporate or freeze within decades. The Terminator would not be a stable paradise. It would be a compromise, a temporary truce between two sides of a hostile world. Yet if any part of Proxima b could harbour life, it is here. A perpetual dusk where daylight never burns and darkness never freezes. A slender path around an alien world, an oasis in a planet of extremes. Proxima b is slightly more massive than Earth. That means stronger surface gravity, enough to make every step feel heavier. Joints strain, tools drop faster. Human muscles would tire as if the world itself were pulling you down. Even a difference of 10 or 15% in surface gravity changes everything. On Earth, you walk effortlessly because your bones, tendons, and muscles evolved in a constant dialogue with our planet's pull. But on Proxima b, every motion becomes negotiation. Climbing stairs feels like wading through wet sand. Carrying supplies turns into labor. A centimeter slip becomes a bone-jarring thud. The gravity isn't lethal, but it is relentless. You don't notice it for the first few minutes. You notice it after 8 hours, when fatigue settles deep in your spine. Space agencies spend decades preparing astronauts for microgravity, but almost no research exists for long-term higher gravity. The body might adapt, but adaptation has limits. Bones grow denser, muscles thicken, and the heart strains harder to pump blood against a steeper gravitational gradient. Standing up from a seated position becomes exercise. Running becomes a challenge of endurance rather than speed. Over time, colonists could become shorter, stockier, with lower centers of mass. Human anatomy would shift to conserve energy, compressing cartilage, tightening ligaments, reinforcing the skeleton. The environment itself would respond to that pull. Mountains would be lower, weather systems slower. Clouds, heavier with moisture, would hang closer to the horizon. Structures must bear extra load, support beams thicker, foundations deeper. A building designed to stand tall on Earth might sag on Proxima b. Even machinery behaves differently. Dropped equipment doesn't arc gracefully, it slams downward. Robots designed to hover or walk efficiently on Earth might burn through energy just to lift their chassis. Gravity influences history on our own planet. Cultures living at high elevations developed powerful hearts and lungs. On Proxima b, these differences would not be subtle. Imagine cities designed horizontally, sprawling outward instead of upward. Elevators become inefficient. Rooftop gardens become burdens. Underground dwellings may be preferable, gravity pressing down, rock reinforcing from above, shielding settlers from radiation and flares while easing structural strain. Plants respond, too. Trees grow shorter and wider, preserving stability. Root systems grip intensely, spreading outward like anchors. Leaves thicken to reduce sag under their own weight. Microbes drift more slowly through air and water. Even flight, if any life has evolved wings, becomes costly. Birds on Earth glide for free once aloft. On Proxima b, they would flap constantly, expending energy simply to stay airborne. Communication changes with gravity. Humans walk slower. Cargo moves in crawlers, not drones. Exploration becomes methodical, measured in patient increments. A child raised here would learn balance differently. They would squat, not leap. They would brace their body before lifting anything. They would grow up thinking Earth's gravity is strange, light, weak, almost playful. The psychological effect is subtle but real. On a heavy world, you are constantly reminded of your body. Every step is labor. Every action has consequence. You are grounded, not metaphorically, but physically. Proxima b forces visitors to respect their own weight. It is a world that does not try to kill you with storms or ice. It simply presses down, quietly, consistently, like a firm hand on your shoulder, reminding you that you are not from here. If Proxima b holds oceans, they would lie beneath a permanent red sky. Waves reflect crimson light, turning water black except near shorelines. Sea organisms, if they evolved, would adapt to an environment lit by a star that glows like a smoldering ember. Light is a sculptor. On Earth, sunlight penetrates water in bands, setting the boundary between surface ecosystems and the deep abyss. Blue wavelengths travel far, red dies quickly. But around Proxima Centauri, the spectrum is reversed. Infrared dominates. The ocean becomes an absorber rather than a mirror. Standing on the shore, you would not see sparkling reflections. You would see the surface swallow the starlight, like velvet swallowing a flame. Beneath the waves, visibility would collapse. On Earth, divers see turquoise gradients and shimmering beams. On Proxima b, you would descend into darkness almost immediately. At just a few meters, the water could turn opaque, like liquid ink. Organisms that live here would not rely on sight. They would rely on pressure changes, chemical gradients, and sound. The ocean becomes an environment of touch and vibration, not color. If life emerged, its metabolism would be tuned to dimness. Photosynthetic organisms might drift near the surface, absorbing red and infrared wavelengths using pigments darker than anything found on Earth. Instead of chlorophyll's green, they might carry molecules that resemble deep maroon or black, optimized to capture every stray photon. Entire reefs could look like obsidian sculptures, alive but invisible until disturbed. Winds from the Terminator zone would generate constant waves, long, low pulses rolling across the sea like breathing. These waves would never receive the full brightness of a sunlit noon. They would only ever know the glow of permanent dusk. The surface might teem with bacteria that harvest energy as heat gradients rather than light. Coating rocks like living soot, their colonies could form mats that pulse slowly with chemical reactions, a biological system designed for scarcity. If predators evolved here, their bodies would not be sleek silver or bright striped patterns. They would be matte and shadow-like. To hunt, they would rely on lateral lines, echolocation, or electric fields. In the endless twilight, movement is information. The creatures that survive are those that feel the presence of prey before the prey feels them. Imagine eel-like forms gliding through black water, detecting a heartbeat from meters away, striking with precision in silence. The shoreline itself would bear signs of this otherworldly ocean. Without sunlight to bleach sand, beaches would be dark, basalt-like, or deep iron red. Tides, driven not by moons but by atmospheric pressure gradients, could sweep high and then recede slowly. Pools left behind would glisten only faintly, like pools of mercury under a dying lamp. If colonists ever walked there, their flashlights would carve tunnels of visibility through air saturated with sea mist. Storms would be slow and theatrical. Clouds forming on the day side would drift toward dusk, condensing into rain over the ocean. Thunder might roll without lightning, energy dissipated through conduction instead of bright discharge. Sheets of vapor could hang over the water for weeks, casting the sea in grey veils that never lift. Life in these seas would not be vibrant, but resilient. It would evolve not to flourish under abundance, but to persist in deprivation. Each organism a testament to adaptation under a sky that never brightens, an ocean that never glimmers, only absorbs, endures, and waits. No sunrise cools the scorched hemisphere. No morning warms the freezing one. Instead, temperature becomes geography. Brutal heat toward the star, brutal cold away from it. Survival depends on distance, not time. On Earth, we are comforted by the clockwork of days. Nights cool, mornings thaw, seasons ebb and return. Proxima b denies this rhythm. Its face toward the star bakes in unending radiation, the rock absorbing energy until it reaches a kind of thermal equilibrium. Not equilibrium in the sense of comfort, equilibrium in the sense of surrender. Temperature rises until there is nowhere left for the heat to go. Cross that landscape, and you enter an environment where every surface is hot simply because it has been hot for millennia. Sand hardens into glass. Dust fuses into ceramic crusts. Water cannot pool. It becomes vapor the moment it reaches exposed land. Metals expand. Tools warp. Structures must be designed to bleed heat constantly, or they fail. Colonists would learn quickly that the best engineering solution is burial. Foundations deep, habitats hidden from the relentless star above. Walk the opposite direction, and you eventually feel the world exhale. Under the permanent darkness of the night side, the lack of light allows heat to radiate into space unopposed. Temperatures fall until molecules slow into rigidity. The air thins, pressure drops. Whatever atmosphere remains becomes sluggish and inert. Frozen plains dominate, stretching outward like an endless polar cap. No dawn ever comes to release the land from its paralysis. Every degree of warmth must be imported, by wind, by geothermal heat, or by artificial means. Between these extremes lies the twilight belt, where temperatures hover somewhere between punishment and mercy. Here, no clock tells the body when to recover or rest. There are no seasons. There is only position. Travel further into daylight, and the heat becomes lethal within hours. Travel too far into darkness, and hypothermia is not a risk but a certainty. Settlements here cannot rely on thermal inertia. Even buildings would require exterior shielding on one side and heaters on the other, each wall designed to withstand a different season forever. The atmosphere reacts to this imbalance with violence. Hot air from the bright hemisphere perpetually rises and rushes toward the cold. Planet-wide storms form not because of rotation, but because of desperation, the world desperately attempting to find equilibrium. Jet streams circle the terminator, dragging heat and vapor in their wake. Imagine a hurricane that never ends, not because it travels across water, but because the entire planet is the fuel. If ice exists, it would stack like armor across the night side. Under pressure, sheets could crack and grind, releasing bursts of methane or trapped gases. Cryovolcanic geysers might erupt in silence, invisible under the starless sky. Without sunlight to melt them, glaciers become geological fixtures, uncut by spring, unbothered by time. Life, if present, would not evolve to tolerate the full hemisphere of heat or cold. It would specialize in gradients. Organisms might migrate slowly, inching toward warmth or retreating toward shadow. Nothing would chase daylight. There is no daylight to chase. Instead, the world demands a new kind of instinct, the ability to sense distance, not hours. On Proxima b, temperature is not a rhythm, it is a map, and every species, native or human, would learn to trace its contours carefully, because even a few steps in the wrong direction could mean a sudden, irreversible end. On the night side, frozen plains may stretch across continents. Ice could reach miles deep, hardened not by winter but by eternal absence of light. This hemisphere is not a season, it is a condition, a place where the ground has forgotten the meaning of thaw. The night side of Proxima b sits beneath a star that never rises, and so heat leaks away infinitely into space. Every night on Earth eventually ends. Even the coldest polar winter ends. But on Proxima b, the darkness is permanent. It turns the planet's surface into a cryosphere, a domain of frozen rock, frozen oceans, frozen air. If you walked across it, your footsteps might echo like strikes against glass. Here, ice is not a veneer. It is architecture. Without solar radiation, every drop of moisture that evaporates from the warmer regions eventually condenses and falls onto the night side. Layer upon layer accumulates. Millennia pass. Ice thickens into continent-spanning shields. What begins as snow becomes packed powder, then compressed crystal, then glacier. Eventually, those glaciers transform into solid blocks that resemble stone more than frozen water. Any buried ocean beneath them would be entombed, insulated from the vacuum of space by miles of refractive frozen mass. Wind, driven by the temperature difference between the hemispheres, arrives here like a slow avalanche of gas. But once it enters the deep cold, it collapses. The air freezes on contact with the ground, forming frost that builds outward in jagged structures. Not flakes, but hoarfrost. Delicate, branching needles of ice crawling across every exposed surface. Without sunlight to sublimate them, these formations would persist for centuries, engraving the night side with crystalline growths that stretch for meters. Geology changes, too. Rock fractures along seams where temperature gradients drive stress. Minerals contract. Dust grains fuse into brittle crusts. Impact craters from ancient meteoroids sit undisturbed, their rims sharpened by cold rather than eroded by rain. Nothing softens them. Even atmospheric erosion slows to a crawl. The night side becomes a museum of geological violence, perfectly preserved, each scar frozen in place. If an atmosphere survives, it would hover low, dense, and still. Above, the sky would be ink black, pierced not by a red sun but by unfamiliar constellations, stars seen from an alien vantage point. Proxima b would orbit its small star while facing away, offering its cryosphere a view of space more static and deep than any night on Earth. Our planet's rotation produces the illusion of shifting skies. Proxima b's locked position would give its darkness an unchanging celestial ceiling. Life here, if it exists, would be shaped by deprivation. They might live beneath the ice, clustered around geothermal vents or deep aquifers. Chemosynthetic microbes could break down minerals, living off gradients of temperature and chemical energy rather than light. Complex life might never surface, only extremophiles endure. For humans, the cryosphere would be deadly in slow motion, not through dramatic storms or violent winds, but through absolute stillness. Equipment would seize, batteries would fail, fabrics would crack. At minus 150 degrees Celsius or lower, metal shears like chalk. Vehicles stall. Frost creeps into joints and seals. Even breath becomes dangerous, freezing moisture on intake valves and respirators. To travel the night side would mean moving through a world sculpted not by time, but by absence. The absence of warmth, of sunlight, of change. A geography of quiet, where the frozen planet waits patiently, indifferent to whatever life might try to claim it. Without a protective magnetosphere, Proxima b would be defenseless against stellar winds. Charged particles would stream into the atmosphere, tearing it apart or altering its chemistry into something alien and toxic. Magnetic fields are invisible shields. We rarely think about Earth's because it works so well. It bends the sun's charged particles and funnels them toward the poles, where they paint the sky with auroras instead of blasting the surface. Beneath that shield, biology flourished. Without it, we would be scorched by radiation. Our atmosphere gradually stripped away like smoke in a gale. On Proxima b, the situation is far worse. Its star erupts constantly, and the planet sits close, well inside the kill zone of stellar aggression. If Proxima b's magnetic field is weak or absent, it is not simply unprotected. It is exposed, every second, to the star's fury. The fragile upper atmosphere becomes the first casualty. High-energy particles crash into the gases, exciting molecules and knocking electrons loose. The air heats unevenly. Some atoms split, some escape entirely. Hydrogen rises and is accelerated outward, lost forever to space. Oxygen fragments into reactive ions that damage whatever remains below. Over millions of years, this constant assault can transform an atmosphere from breathable to corrosive, and eventually to non-existent. The difference between a living planet and a dead rock may come down to whether it can hold on to its own air. Earth's magnetosphere exists because our core churns like a dynamo, molten iron and nickel swirling beneath our feet. Scientists are uncertain whether Proxima b can maintain a similar engine. A planet slightly larger than Earth may have more internal heat, more radioactive decay, and more potential for liquid metals. But tidal locking complicates everything. The gravitational grip of the star may slow internal convection. A frozen core produces silence, not a shield. In that case, the planet becomes an open target for cosmic weather. Radiation also rewrites chemistry in subtle ways. Ultraviolet and X-rays bombard molecules in the atmosphere, splitting them into radicals that recombine with new partners. Nitrogen pairs with oxygen to form ozone, then breaks apart in the next flare. Carbon dioxide fractures into carbon monoxide. Methane, if it ever existed, doesn't last. The result is an atmosphere constantly shifting between toxic equilibria. A planet like this can never truly recover. It is always responding to the last disaster, never preparing for the next. A weak magnetic field would leave the surface even more vulnerable. Radiation doesn't just damage tissue, it attacks information. DNA mutates. Cellular machinery fails. On Earth, these mutations are rare enough to fuel evolution. On Proxima b, they may come faster than any organism can repair. Life, if present, must burrow deep, into oceans, lava tubes, or caverns where thick rock becomes surrogate shielding. Human explorers would not trust the sky. Every habitat would require layered protection. Outer walls of regolith, inner shells of composite, radiation traps embedded in the structure. Colonists would live beneath domes that have never seen direct starlight. Satellites would burn out in months. Even communication arrays would degrade under constant bombardment. Proxima b may be a world of oceans and ice, stone and wind. But if it lacks a magnetic heart, its fate is written in its star. The cosmos does not spare planets for being promising. It judges them by whether they can defend themselves. If life evolved, it might retreat downward. Subsurface oceans, caves, or aquifers shield organisms from radiation. On Proxima b, survival may mean living beneath rock, an entire ecosystem hiding from the sky. The surface of the daylight hemisphere is a battleground. Radiation storms hammer the land without warning. Flares carve the atmosphere like invisible blades. In that environment, evolution has two choices: endure the constant assault or step out of the line of fire. Underground, even a few meters of rock can block the most damaging waves. Tunnels, crevices, basalt chambers. These may be more than geology. They may be refuges, cradles of biological persistence carved by eons of desperation. On Earth, we see a hint of this strategy in extremophiles. Microbes thrive deep underground, far from sunlight, living off chemical gradients in porous rock. They metabolize minerals, sulfur, hydrogen, iron. They inhabit places where time slows and conditions change only over millennia. On Proxima b, similar forms might represent not specialized oddities, but the dominant branch of life. Evolution would favor organisms that accept the darkness, trading light for stability. If Proxima b ever held oceans, the most resilient life may have retreated beneath their floors. Hydrothermal vents could provide energy through chemical reactions, not photons. Superheated minerals mixing with colder waters generate gradients rich enough to sustain communities. On Earth's seafloor, creatures gather around black smokers in total darkness. Their ecosystems are ancient, indifferent to sunlight. Imagine that principle scaled to a planet where darkness is not a niche, where it is the rule. Caves on the night side would be even more isolated. There, cold dominates, but ice itself can insulate. Layers of frozen rock trap geothermal warmth, creating pockets where temperatures hover above freezing. Water trickles through fractures, carrying dissolved minerals. Microbes might colonize those cavities, forming mats along stone. Their metabolism slow but steady. Life here would not bloom. It would persist. It would measure success, not in generations, but in geological epochs. For hypothetical intelligent settlers, human or otherwise, underground would be the only sensible frontier. Structures built on the surface would need constant shielding and maintenance. Radiation shelters would draw enormous power. Beneath the crust, stone does the work. Cities might stretch horizontally through lava tubes, branching like roots. Homes carved into ridges bathed in geothermal heat. Transportation networks constructed not under skies, but under ceilings of basalt, quartz, and iron. The atmosphere above could rage, the star could flare, and life below would barely notice. Vegetation, if it existed underground, would not resemble forests or fields. It might consist of biofilms lining cavern walls, symbiotic lichens feeding off minerals, or fungi-like forms spreading through fractured rock. Their energy sources would be indirect, oxidizing iron, absorbing chemical traces from groundwater, or harvesting heat from subsurface vents. Bioluminescence could emerge not as decoration, but as communication. A slow pulse of warning or reproduction, echoing through the dark. Explorers on Proxima b would learn humility quickly. They would descend not to mine resources, but to escape the sky. They would rely on subterranean reservoirs, tapping aquifers that have never seen starlight. Most importantly, they would adapt to a way of life where the planet becomes ceiling, shield, and habitat all at once. In this world, the surface is a battlefield. The underground is home. A planet that looks hostile from orbit may be gentle beneath its own crust, its ecosystems folded away, alive not because they conquered the star, but because they learned to hide from it. Light on Proxima b is red-rich and blue-poor. Plants like Earth's could starve. Life here would need pigments that absorb infrared, perhaps dark purple or nearly black, absorbing every photon like a cosmic sponge. On Earth, chlorophyll thrives because our sun saturates the surface with blue and green wavelengths. Plants reflect the green they do not need, which gives them their familiar color. Photosynthesis is a negotiation between efficiency and protection. Absorb enough energy to grow, but not so much that cells overheat or burn. On Proxima b, the negotiation begins with scarcity. Its star glows weakly compared to our sun. The radiant power trickling through its atmosphere is not a flood, it is a drizzle. For life to capture meaningful energy, pigments must be aggressive rather than selective. Infrared wavelengths carry less energy per photon. A pigment designed to use them would have to trap many more photons to perform the same chemical work chlorophyll does on Earth. That need drives evolution toward deeper colors, pigments that absorb rather than reflect. Imagine fields of black plants stretching across the twilight belt, their leaves dull and matte, drinking radiation silently. Under Proxima's crimson sky, these organisms would not gleam. They would vanish into the landscape, indistinguishable from volcanic rock, until the wind brushed them or they rippled in motion. But alien photosynthesis may split into multiple strategies. Some organisms could live in shallow soil, storing radiation as heat, then using enzymatic catalysts to convert that stored energy into chemical bonds. Others might cluster around geothermal vents, using the star as a supplemental source rather than a primary one. Life might not treat sunlight as a daily necessity. It might treat it as a luxury, a small bonus layered onto a metabolism built for darkness. On Earth, cyanobacteria helped oxygenate our atmosphere and pave the way for complex life. On Proxima b, their counterparts, if they exist, would have very different biochemistry. Their pigments could be optimized to collect every scrap of energy, making them dangerously vulnerable to flares. A sudden burst of high-energy light might fry their tissues unless they evolved shielding or rapid repair mechanisms. Instead of growing taller or wider, these organisms might lie flat against the ground, minimizing exposure, forming living crusts that expand centimeter by centimeter over centuries. Photosynthesis may even move underground. Cracks in basalt, crevices in fractured cliff faces, or porous sediments could serve as refuges where only filtered infrared reaches. Organisms would stretch thin networks of filaments toward those faint beams, harvesting what they can while sheltered from lethal radiation bursts. Their colonies would resemble veins running through stone, biological circuitry channeling light into survival. If larger plant-like forms emerge, they would not sway in open fields. Their shapes would be compact, armored, with thick cuticles to prevent moisture loss in thin or violent atmospheres. Their root systems would burrow deep to reach mineral-rich layers, feeding not only on photons but on dissolved metals and salts. They might store energy in dense carbohydrates or waxy hydrocarbons, fueling slow, deliberate growth during periods of calm star behavior. Imagine walking through such a biosphere. There is no green. The terrain is a palette of greys, maroons, and obsidian hues. Leaves feel heavy, rubbery, almost artificial. When sunlight touches them, there is no shimmer, only absorption. A planet-wide silence of energy conversion, invisible to the eye yet essential to survival. On Proxima b, photosynthesis is not an expression of abundance. It is an act of desperation, life reaching for the faintest embers of a star that never truly shines. Flares explode in seconds, but their effects can last days. Radiation could ionize air, triggering auroras that blanket the entire dayside. Not gentle green curtains, intense, violent sheets of light rippling across the sky. On Earth, auroras are a rare spectacle tied to geomagnetic storms and polar regions. On Proxima b, they might be the sky's default state. Each flare from the star ejects torrents of charged particles, protons, electrons, and heavier ions at extreme velocities. These particles slam into the planet's upper atmosphere like a cosmic hurricane. Under Proxima's relentless bombardment, the electromagnetic quiet we consider normal may simply not exist. Instead, the atmosphere becomes a canvas, constantly rewritten by invisible storms. When these particles strike, they inject energy into the gases above the surface. Atoms absorb the assault, become excited, and then release photons in response. The glow is not delicate or fleeting. It is jagged and forceful, stretching from horizon to horizon. The auroras would not trace elegant ribbons. They would appear as sweeping walls, violent smears of red, violet, and ultraviolet brilliance. They could pulse rhythmically, like the heartbeat of an angry star, painting the sky with the signature of every flare. For anyone on the surface, this spectacle would serve as a warning. The beauty is deceptive. These light displays mark regions where radiation levels spike dangerously high. An unshielded observer would feel none of the drama, only fatigue, cellular damage, and sickness. Radiation penetrating tissue, corrupting DNA, shortening lifespans with every exposure. On Earth, auroras represent wonder. On Proxima b, they might represent survival thresholds. The storms can reach the atmosphere quickly. Solar wind from Proxima Centauri would arrive in a matter of minutes, not days, because of the planet's close orbit. During a major flare, the exosphere could inflate like a balloon, expanding outward into space. The atmosphere might literally breathe in and out, stretching into tenuous vapor, then collapsing back. Satellite or drone infrastructure would be torn apart by the fluctuations. Communication pulses would scatter. Navigation systems could lose calibration. The planet becomes momentarily chaotic, then settles back into its quiet tension until the next flare hits. The ground experiences effects too. Ionized particles entering the atmosphere create electric imbalances. Static charges accumulate across surfaces. Dust and sand could lift into the air, driven by electrostatic force instead of wind. Rocks spark, equipment shorts. Explorers could see arcs of light crawling across metal like living tendrils. Even protective suits might not be enough. Insulation designed for simple heat and cold must now resist cosmic lightning. Large flares from red dwarfs are not polite single events. They cluster. A star like Proxima can erupt repeatedly, compounding damage. One flare weakens atmospheric molecules, another strips them, a third drives them into space. The storms link together into a chain reaction. Eventually, the atmosphere may erode faster than geological or volcanic processes can replenish it. On an inhabited world, intelligent life might respond in one of two ways: advance downward or build upward. Cities could sit underground, shielded by rock, connected by tunnels, or they might sit behind massive electromagnetic shields, technological auroras built to counter the sky's natural violence. Either option is expensive. Either option admits a truth. Life on Proxima b would always be negotiating with its star. There is no calm season here. There is only the quiet interval between flares, a silence that ends without warning, when the sky erupts again in sheets of light and the planet holds its breath. Proxima b may once have been Earth-like, oceans evaporating into storms, rain cycling through basaltic plains, clouds drifting across a tidally spinning surface. But billions of years under a hostile star may have erased those memories forever. In its youth, Proxima Centauri burned brighter and flared more violently than it does today. Red dwarfs pass through prolonged temperamental phases, unleashing energies that dwarf even the most powerful solar storms we've seen from our sun. If Proxima b was born with oceans, vast basins of salt water pressed against volcanic coastlines, its early climate might have resembled Earth's primordial chaos. Water currents would churn, rainfall would carve channels through raw basalt, rivers would split into deltas and fill shallow seas. Cloud systems would rise, condense, and fall again, cycling minerals from mountains to ocean floors. For a time, the planet might have been a watery refuge, shielded by its distance from a still-forming star, but that period would not last. Once Proxima Centauri entered its flare-dominated adolescence, atmospheric erosion would accelerate. Flares are more than bursts of light. They are engines of destruction. They produce high-energy ultraviolet and X-ray radiation capable of peeling apart water molecules, catalyzing the escape of hydrogen into space. As hydrogen fled upward, oxygen remained behind, forming unstable compounds that poisoned the atmosphere. The balance of gases changed. Rain grew acidic, storms grew violent. The hydrosphere, once a reservoir of life, became ammunition for atmospheric loss. Over millions of years, oceans shrink. They do not disappear all at once. They recede. The first casualties are shallows and estuaries, then inland seas, then coastlines. What remains pulls away from the star-facing hemisphere, fleeing evaporation into deeper planetary basins. A world that once shimmered blue becomes pocked with inland salt flats and cracked mud beds. The twilight zone becomes the only refuge for liquid water, a narrow strip where temperatures allow droplets to fall and rivers still flow. Eventually, even that strip may fail. Water cycles stop not because rain ceases, but because condensation can no longer happen. Without a sufficient atmosphere, air cannot hold moisture. Droplets do not form, clouds do not bloom. Surface winds scour the landscape, lifting dust instead of mist. The planet becomes quieter, not because it is calm, but because it has lost its medium of weather. The wind blows, but nothing condenses, nothing falls. The hydrological engine that once carved canyons and nourished life becomes a fossil, an ancient memory carved into the terrain. The oceans, if they remain at all, migrate downward. They descend into fractures and porous stone, locked beneath ice or trapped beneath pressurized rock layers. Subsurface aquifers become the last vaults of liquid water, cold and ancient. They may hold chemical relics of earlier ecosystems, microbial spores, dormant life, or mineral signatures that whisper of a time when sunlight still touched waves. For explorers or scientists arriving millennia later, Proxima b would be a puzzle of absence. They would see scars, widened canyons, eroded deltas, sedimentary layers laid down by water long vanished, basalt plains polished by waves, fossilized ripples preserved in rock, stretching across valley floors that have not tasted moisture in eons. The planet itself would tell the story. Quietly, stubbornly, without a single drop of water left to speak for it. If Proxima b ever knew Earth-like seas, they are not lost in myth, they are lost to physics. Not in dramatic collapse, but in slow, patient erosion by a star that never cared what bloomed beneath its light. Stars like Proxima Centauri live for trillions of years. That means more time for life to arise. But their violent early phase and unstable energy output could sterilize young planets long before life has a chance to begin. Red dwarfs are cosmic contradictions wrapped in dim light. They are the smallest class of stars capable of nuclear fusion, fusing hydrogen at an astonishingly slow rate. Their fuel consumption is so conservative that they never race toward death like sun-like stars do. Instead, they burn with patience. A red dwarf could outlive every planet in our solar system, every civilization that will ever walk Earth, and still be young compared to its stellar siblings. In terms of time, they are the ultimate incubators, light that refuses to die. But longevity is not the same as stability. In their youth, red dwarfs behave like cosmic tantrum machines. Their cores churn unevenly. Magnetic fields knot and snap. They flare unpredictably, ejecting bursts of radiation that dwarf anything our sun produces. A young red dwarf can release enough ultraviolet and X-ray energy in minutes to strip atmospheres from nearby planets. For billions of years, these eruptions occur not occasionally, but regularly. Any nascent biosphere braving those conditions must survive, not seasons of instability, but eras of it. This is the paradox. The longest-lived stars may create the least forgiving environments. Planets, in the habitable zone of a red dwarf, must orbit close, sometimes closer than Mercury orbits the Sun. That proximity intensifies the storm. It locks planets tidally, forcing one face to permanently face the star and the other to remain frozen in endless darkness. Habitability becomes a narrow question. Can life endure on the thin twilight band between inferno and ice? And even if conditions there are marginally survivable, the star overhead does not respect that fragility. Earth's biosphere flourished in stability. Our sun calmed early and remained gentle. Red dwarfs never truly grow up. Even ancient ones continue to flicker and erupt. Proxima Centauri is over 4.8 billion years old, older than the Sun, and yet its flares remain powerful enough to strip atmospheres and scorch the surface of Proxima b. This is not a youthful phase. It is a lifestyle. But paradoxically, if life endures the first few billion years, it might inherit eternity. Imagine a world that survives. Perhaps it forms a thick magnetosphere, generated by a churning iron core, or perhaps its atmosphere becomes dense enough, like Venus, to resist erosion. Life might hide underwater or underground until the star settles into a quieter adulthood. Once it does, the system becomes an oasis of stability. No expanding star to engulf planets, no impending death in a few billion years. Just slow-burning light, century after century, million after million, breathing softly. Civilizations built around red dwarfs would have time unknown to species like ours. They could observe entire galaxies drift apart, evolve across cosmic epochs, and still watch their star flicker patiently. It is a strange irony. The universe's most abundant stars may foster life only when it has already learned how to survive catastrophe. That is the lesson of Proxima Centauri. Longevity is hope, but hope must first survive the fire. Proxima is not alone. It wanders in orbit around Alpha Centauri A and B, two larger stars. Their distant gravity tugs subtly at Proxima b, shifting its orbit over millennia, introducing long-term climate cycles hidden beneath calm skies. To the human eye, Proxima Centauri appears like a solitary ember in the sky. But astronomically, it is the outlier member of a gravitational family. Alpha Centauri A and B orbit each other like a stellar duet. Bright, stable, almost sun-like. Proxima trails them at an extraordinary distance, circling slowly on an orbit that takes centuries just to complete a fraction of its loop. Imagine a planet whose sun is already violent and unpredictable, now further influenced by two distant giants that bend the shape of its orbit without ever being seen from its surface. Gravity is subtle, but it is relentless. Even at distances measured in tens of thousands of astronomical units, the pull of Alpha Centauri A and B accumulates. Over millions of years, their influence changes Proxima's orbit, drawing it closer, pushing it farther, tilting its path. Proxima b, caught in this gravitational ballet, feels those changes indirectly. When Proxima approaches the pair, its own orbital zone compresses slightly. Radiation increases. Stellar winds strengthen. When it drifts farther away, the environment relaxes. The climate might stabilize for centuries, only to destabilize again when the next cycle begins. These shifts are not dramatic like seasons or storms, they are slow climate pulses. A world like Proxima b may experience epochs of relative calm and epochs of intensifying atmospheric erosion. Oceans could shrink or expand depending on how much stellar energy the planet receives. Ice caps, if they exist, could advance across continents over tens of thousands of years, then retreat. On Earth, ice ages respond to slight variations in orbital eccentricity. Proxima b experiences that same principle, magnified by stellar neighbors that outweigh its star dozens of times over. In the twilight belt, these changes might be subtle at first, temperature gradients shifting, cloud systems migrating, rainfall patterns altering. Over millennia, that zone of habitability could drift. A settlement built in one era might become unbearably hot or dangerously cold in another. On Proxima b, civilization wouldn't track its history in centuries, but in gravitational cycles, epochs when Alpha Centauri's pull grows strong and epochs when it diminishes. There is also the question of cometary influx. When Proxima moves closer to its sister stars, their gravity may disturb surrounding debris clouds. Comets, asteroids, and icy fragments could be nudged inward. Impact rates might surge. If the planet once held oceans, meteor bombardment could have returned water intermittently or destroyed it in bursts of vaporization. Worlds do not evolve in isolation. They evolve at the mercy of their celestial neighborhoods. From the planet's surface, these distant suns would appear faint, never rising like second or third moons. Their influence is not visual, but structural. A civilization researching its own climate might have no idea why long-term patterns shift. The changes would unfold too slowly to perceive. Only orbit modeling and star mapping could reveal the truth. The world is shaped not only by its star, but by stars it cannot even see. And that is the quiet danger of a triple system. The planet may have survived Proxima's worst storms. It may have guarded its atmosphere, sheltered life in oceans or caves. But gravity is patient. Even if the star softens, the cosmos has other levers. Proxima b exists at the intersection of three bodies, each exerting force over millions of years. Not a world governed by one sun, but by three, arguing silently over its fate. Traveling from our solar system to Proxima's is like crossing an ocean without stars. No gas stations, no refueling points, no gravitational shortcuts, only emptiness, radiation, and the constant struggle against inertia. We often imagine space as a void dotted with points of light, but the gap between stellar systems is not a gentle distance, it is space at its most hostile. Voyager 1, humanity's fastest emissary to leave the solar system, would need more than 70,000 years to reach Proxima Centauri. That is longer than recorded human history. Even if we built a craft 10 times faster, the journey would still span thousands of generations. Interstellar space is not a road we travel, it is a gulf we endure. The space between stars is not truly empty. It is filled with tiny hazards, dust particles, cosmic rays, stray atoms accelerated to relativistic speeds. A grain of sand in the void, struck at 1/10 the speed of light, has the power of artillery. A vehicle built to cross that gulf would need shielding thicker than starship fiction imagines. It would be a bunker with engines, a vessel built less like an airplane and more like a slow-moving fortress. Light itself is diluted in interstellar space. After leaving home, a traveler would watch the sun shrink into a single bright star, then a spark, then just another point in an indifferent sky. Ahead, Proxima's red glow would remain invisible until the final segment of the journey. For decades or centuries, the view outside the window would never change. A black ocean extending forever, in every direction, punctuated only by distant constellations that offer no warmth and no refuge. On Earth, we measure time in hours, days, and seasons. In interstellar transit, time becomes the distance between stars. Energy is the defining problem. Chemical fuel is impossible. Nuclear fission barely scratches the surface. Fusion or antimatter propulsion might shorten the journey, but neither exists at the scale required. Even with optimistic estimates, accelerating to a meaningful fraction of light speed demands more energy than entire nations produce, and accelerating is only half the battle. The ship must slow down without colliding with Proxima, or overshooting it into eternal drift. Gravity wells, a staple of science fiction, offer little help in reality. Between stars, there are no convenient planets to slingshot around. The nearest masses are light years apart. A spacecraft heading toward Proxima must rely on its own momentum, pushing against resistance that cannot be seen or measured in familiar ways. Tiny cosmic dust becomes the enemy. Micrometeorites, the snipers of the void. Even cosmic radiation becomes a slow poison for electronics and genetic material. Psychology may be the cruelest challenge of all. A vessel carrying generations of passengers is a world unto itself. Their children and grandchildren would live and die inside a ship whose destination they will never see. There is no horizon that draws closer. There is no sunrise to mark the progress. The stars ahead drift so slowly that motion becomes theoretical. Humans evolved to follow rhythms, daylight, seasons, tides. Interstellar transit strips those rhythms away and replaces them with the measured heartbeat of engines. The greatest irony is that Proxima is not impossibly far. Cosmically, it is next door, but the space in between is ruthless. It does not invite exploration, it questions it, and before we can ever set foot on Proxima b, we must first conquer the silence between suns, a silence so immense that, for now, it has only ever been crossed by light. Human probes like Voyager move at incredible speeds, but even they would require tens of thousands of years to reach Proxima. A journey that looks short on paper is, in practice. Voyager 1 left Earth in 1977. Propelled by planetary slingshots and human ambition, it crossed the edge of the heliosphere in 2012, entering the interstellar medium, an environment no machine had ever touched before. We often talk about Voyager as though it is still traveling through our neighborhood. But the truth is harsher. Voyager is barely outside the front porch. Its current path is measurable in thousands of astronomical units, yet Proxima Centauri lies more than 266,000 astronomical units beyond. The probe will drift through darkness long after every human alive today has faded from memory. It carries a golden record, a message carved into metal. Sounds, greetings, music, diagrams. Voyager travels at nearly 38,000 miles per hour. That is fast enough to circle Earth in less than an hour. In interstellar terms, it is crawling. If it were aimed directly at Proxima, it would still need more than 70,000 years to get there. Civilization would rise and crumble dozens of times before the probe arrived. Entire languages would vanish. Continents would redraw themselves. Humanity might not even exist by the time it reaches its silent destination. Voyager is not a ship. It is a message in a bottle tossed into the cosmic ocean. It does not slow. It does not search. It does not navigate. It will drift until entropy claims its circuitry. Even if an alien civilization discovered it, they would find a husk, a machine that has long since lost power, carrying memories in patterns they might never decipher. The golden record is a relic of optimism, not an invitation. The same reality confronts every mission we imagine. A spacecraft that leaves Earth tomorrow, built with our best propulsion systems, would still take longer than recorded human history to reach Proxima, and that assumes everything goes perfectly. No mechanical failures, no fuel shortages, no micrometeoroid impacts. Interstellar travel magnifies every risk. One failure is final. One crack in shielding becomes a death sentence at relativistic velocity. Voyager itself is already running out of voice. Its instruments are shutting down, one by one, sacrificed to conserve the power that remains in its radioactive heart. Deep space network receivers strain to catch its faint signals, photons that took 22 hours to cross the void. There will come a day, soon, when Voyager speaks for the last time. Not because it stopped moving, but because the universe drowned its whisper. And yet, the probe still matters. It is the first human-made object to leave the solar system. It carries proof that we once looked outward and dared to send something into the unknown. It reminds us of our scale, small, fragile, and curious. Voyager is humanity's first step beyond the sun, not because it will reach another star, but because it proves we can send something into interstellar darkness and let it go. If 1,000,000 years from now someone intercepts the craft, they will not find our technology, they will find our intent. A small machine drifting silently between suns, carrying the simple truth that a species on a blue planet once wanted to be heard. While we debate, Proxima b continues its tight orbit every 11.2 Earth days. It completes dozens of years in the time we complete one. A world in fast motion beneath a star that burns slowly through epochs. On Earth, we are creatures of clocks. Our bodies obey 24-hour cycles. Our calendars trace months and seasons. We measure progress with birthdays, anniversaries, graduations. Proxima b rejects those rhythms. Its orbital year is not a celebration. It is a blink. The planet circles its star in less than 2 weeks, its velocity whipped around Proxima Centauri by intense gravitational pull. To live there would mean learning new patterns of existence, scaling life down to relentless cadence, 1 Proxima b year per lunar cycle. The paradox deepens when we consider its sun. Proxima Centauri burns so slowly that it will remain alive trillions of years beyond our sun's death. The planet races while its star lounges through eternity. On Earth, a single orbit is a trip around a star that will one day consume its worlds. On Proxima b, dozens of orbits barely register in a stellar heartbeat. Time moves like a gear system with mismatched teeth, one wheel spinning wildly, the other turning nearly still. This tension is not abstract. It affects climate cycles, geology, and biology. If clouds form on the day side, they will sweep across the Terminator Strip in mere days before condensing or evaporating again. Small shifts in atmospheric density could take place over thousands of orbits. Tidal flexing, the slow kneading of a planet's crust due to its proximity to a star, could deform the rocks on a timescale far faster than Earth experiences plate motion. What we call geological time may feel almost rhythmic there. Imagine societies trying to chart history on Proxima b. An empire could rise and fall in years, numbered in the tens of thousands. Not because time passed quickly, but because their calendar moved at hyperspeed. A child growing up would accumulate hundreds of planetary years before adulthood. Philosophers might have to invent different languages to describe time, measures of day-night contrast, cycles of stellar calm. On Proxima b, cosmic time would refuse to align with human instinct. For scientists observing from Earth, the planet's orbit is a reminder that we are outsiders. We watch it whirl around its star at a pace we cannot experience. Telescopes witness one orbit after another, storm after storm, flare after flare, while our institutions crawl through research cycles measured in decades. The planet is impatient. Humanity is not. We are waiting for new technology, waiting for propulsion, waiting for instruments powerful enough to taste its atmosphere remotely. Meanwhile, Proxima b continues to loop through its short year, like a bead on a cosmic string. Humans often speak of exploration as destiny. The truth is slower. Interstellar science proceeds on timelines our biology cannot comfortably perceive. We want answers within our own lifetimes. But the universe does not hurry for us. Even if we launched a probe tomorrow capable of traveling faster than any spacecraft ever built, We would die before it reached the halfway point. That does not make the mission meaningless. It makes it monumental. Proxima b teaches patience. In its sky, nothing changes quickly. In its orbit, everything changes constantly. It is a reminder that time is relative not only in Einstein's sense, but in a human sense. The universe will wait for us, but it will not slow down. To make Proxima b habitable, humanity would need global magnetospheres, atmospheric factories, and radiation shelters. Terraforming would not be landscaping. It would be surgery performed on a planet scarred by its own sun. Terraforming Mars is often depicted as an engineering challenge, a complex but imaginable process of warming a cold desert and thickening a thin sky. Its danger is not the absence of warmth, it is the constant presence of violence. Before we could build cities or plant crops, we would have to protect the planet itself from the star it orbits. Every breath of air, every drop of water, every living cell would need shielding. Terraformation becomes triage. The first challenge is radiation. Without a magnetosphere, Proxima b stands naked against stellar winds. To compensate, humanity might construct artificial magnetic shields, enormous structures anchored in orbit. These would generate planetary-scale magnetic fields designed to deflect charged particles away from the surface. Such a system would not resemble satellites. It would be a global exoskeleton, powered by massive reactors or superconducting loops. The shield would need to run continuously. One lapse, and the star's next flare could undo a century of work. Then comes the atmosphere. If Proxima b has already lost its original air, we would need to build a new one. That is not a matter of pumping oxygen into the sky. Atmospheric engineering would require greenhouse gases that trap heat without breaking down under ultraviolet bombardment. Factories might release engineered molecules, fluorocarbons, sulfur compounds, or tailored aerosols designed to capture warmth and resist ionization. Terraformers would not sculpt landscapes with water. They would sculpt chemistry with patience. Temperature gradients present another obstacle. The planet's tidally locked nature ensures one hemisphere bakes and one freezes. Instead, solutions must bridge the two hemispheres. Perhaps we build heat transfer systems, vast oceanic pipelines carrying warm water into the dark, or atmospheric pumps distributing energy across the terminator zone. The twilight belt becomes the most valuable real estate in the galaxy, a region where delicate equilibrium could bloom. Cities might form in a ring, stretching around the planet's circumference, feeding off controlled climate and consistent temperature. Even with such feats, radiation shelters would remain necessary. Colonies would likely be underground, protected beneath meters of basalt. Surface settlements would exist only during stellar calm, with retractable shields ready to deploy when flare alerts sound. You could imagine entire towns moving like turtles, retracting their solar arrays and antennae whenever the sky is about to burn. Terraforming here is less making Earth 2 and more building a defensive organism around a wounded world. And then there is biology. Any Earth-based species introduced to Proxima b would face a different spectrum of light and temperature. Crops must be engineered to function under red suns. Their cells must tolerate radiation bursts and slow growth cycles. Trees would need thicker trunks to survive high gravity. Aquatic organisms would require pigment systems tuned to infrared wavelengths. Terraforming does not end with engineering. It must also rewrite life. The final complication is time. We measure terraforming projects in centuries. Proxima b asks for millennia. Each generation would work toward a goal none of its citizens would live to see. The planet would resist every attempt, not maliciously, but mechanically, its physics and star constantly tearing down what we build. Terraforming a blood-red world is not a dream of shaping land beneath an alien sun. It is a test of endurance, a negotiation with a star that never stops flaring, a planet that refuses to rotate, and a universe that does not care whether we succeed. Only the patient would attempt it, and only the stubborn would stay. We have scanned Proxima b. We have searched for artificial radio bursts, narrowband transmissions, alien signatures. The silence is profound. Either nothing lives there, or what lives there has no reason to speak to us. For decades, we've pointed dishes and antennas toward Proxima, straining to hear whispers from our nearest neighbor. SETI arrays sweep the sky in narrowband windows, looking for patterns that nature does not create. Repeated pulses, non-random timing, modulated carriers. The logic is simple. If an intelligent civilization exists, it might use radio because radio crosses space efficiently. But Proxima has answered us with nothing more than the low hiss of stellar wind. If life exists there, it is either uncommunicative or unreachable. Silence, however, is ambiguous. It does not mean absence. It could mean technology we cannot detect. A species evolving beneath radiation shelters might use communication methods totally foreign to us. Neutrino streams, laser pulses hugging the planet's atmosphere, tight beam optical channels never intended to leak into space. They might talk along fiber-like biological networks, or they might not communicate globally at all. If their world is carved by constant threat, civilization could look like clusters of isolated populations, each sealed beneath stone, with no incentive to broadcast their presence. There is also the possibility that intelligent life, if it ever rose on Proxima b, did not survive the flares. Evolution is a negotiation between potential and punishment. Red dwarf systems punish hard. If early ecosystems flourished during a calmer epoch, their successors may have been vaporized when the star's activity intensified. Civilizations born underground might never develop astronomy. They would navigate by geothermal heat, not constellations. They might know their world intimately but remain ignorant of the cosmos above, never discovering radio, never understanding stars beyond the one that scars their home. Scientists have also learned to fear false alarms. In 2019, a narrowband transmission was detected from the direction of Proxima. It was structured and artificial, everything SETI hoped for. The world held its breath, and then, slowly, painfully, the evidence collapsed under scrutiny. It was a human signal bouncing off hardware, masquerading as alien intelligence. Disappointment stung, but it also revealed a deeper truth. Communication is fragile. One stray reflection can fool our best systems. A real signal, faint and intermittent, could hide in that clutter like a whisper behind static. Even if a civilization wanted to communicate, why would it reach out to us at all? On Proxima b, survival is not a philosophical exercise. It is daily engineering. A species that spends its existence burrowed underground, shielding itself from ultraviolet storms, might see communication as wasteful. They might face existential threats so persistent that contacting distant stars feels as pointless as a drowning sailor sending letters. And then there is fear. On Earth, silence is sometimes prudent. Not everyone who listens is a friend. A species orbiting a temperamental red dwarf might learn early that the universe is hostile. The lesson could be simple. Remain unseen. Broadcast nothing. Do not risk inviting anything that could take your refuge away. Proxima b sits just over 4 light-years from us, close enough that our signals already wash across its skies like invisible tides. If intelligence lives there, it has already heard us. And if it has chosen not to answer, that silence may be the most revealing message of all. If we ever colonize its terminator zone, our cities might stretch along a single planetary ring, following eternal twilight. Streets lit by red dayglow on one side and ice-black night on the other. Such a settlement would look nothing like the layered metropolises we know on Earth. Rather than spreading outward in all directions, It would ribbon around the circumference of Proxima b like a belt, narrow, cautious, and precise. The twilight zone is not expansive. It is a transitional strip only wide enough to balance heat from one hemisphere and cold from the other. Colonists would live where a few degrees of temperature keep water liquid, where the soil, if any, is not frozen or scorched. In this fragile equilibrium, cities would grow sideways, following the curvature of the planet. Buildings would hug the ground. Towers are inefficient under higher gravity and constant wind shear. Instead, habitats would sink beneath protective crust. Surface structures might resemble flattened domes or aerodynamic shells, each layered in basalt shielding, radiation-resistant polymers, and reflective plating. On the dayside walls, heat exchangers would bleed warmth away. On the nightside walls, heaters and thermal reservoirs would push energy back in. Every room would be a negotiation between two extremes. Transportation infrastructure would mirror the environment. Railways or maglev lines would run laterally along the twilight belt, not across it. Traveling outward, to the day or night hemispheres, would be risky. Supply vehicles venturing too far toward daylight could overheat and melt. Those heading into deep night could freeze and seize. Explorers would move with deep caution. A few kilometers too far in either direction could become fatal. The route around the planet would be the only stable corridor, an artery of survival linking research outposts, agriculture modules, and thermal power stations. Agriculture would be its own science. Crops may need engineered photosynthetic systems tuned to infrared, with pigments black or deep maroon. Even then, farming on the surface would be risky. Flares could sterilize fields in minutes. Most food production would shift underground, hydroponic vaults beneath meters of rock illuminated by artificial red spectrum grow lamps. Bioengineered fungi and bacterial cultures would anchor the food chain. Livestock, if ever feasible, would be miniature and resilient, hardy species that thrive under limited light and high pressure. Energy systems would be hybrid. Solar collectors on the bright-facing side would capture radiant heat, not just visible light. Meanwhile, geothermal taps would pull from the crust, where tidal forces may have warmed subsurface layers. Wind turbines in the twilight zone could spin constantly, driven by temperature imbalance, one hemisphere forcing air toward the other in atmospheric cycles that never end. Daily life would be shaped by vigilance. The sky, visible through filtered windows, would be neither blue nor black but a permanent copper haze. Children would grow up watching the division, one horizon glowing red, the other swallowing light entirely. They would learn early where safety ends, where sunlight turns lethal, or where cold begins to suffocate. Their games would be linear, their streets linear, their maps linear. Governance, too, would adapt. Cities stretched in a ring do not form centers. They form chains. Authority would decentralize into districts linked by transit, each section responsible for its portion of infrastructure. Communication networks would hum through fiber lines buried beneath stone. Culture might evolve around the rhythm of the planet. Warm-side engineers, cold-side miners, twilight farmers. Communities would bond not by borders but by gradients. A settlement on Proxima b would be an act of humility, not a conquest of a world, but a narrow compromise with it. Humanity's first interstellar city would not be a monument to triumph, but a quiet ribbon of civilization carved along the edge where life is barely possible. An ember burning between fire and frost. Proxima b may show how fragile habitable worlds are. A slight shift in radiation, a magnetic lapse, a star's mood swing, and oceans vanish. Atmospheres die. Civilizations never form. It is a warning whispered from just next door. We often imagine Earth as resilient because it has supported life for billions of years. But habitability is not destiny. It's luck layered upon physics. Our atmosphere exists because our core spins. Our oceans exist because our sun calmed early. Our magnetosphere exists because molten metals still churn beneath our crust. Strip away any one of those conditions, and our world might resemble Proxima b, a planet sculpted by loss rather than potential. The universe does not reward life. It tolerates it, briefly, when conditions align. The tragedies of distant worlds are not theoretical. Mars once held rivers that carved deltas and lakes that pooled in ancient basins. Venus may have hosted oceans before its greenhouse turned catastrophic. Both now stand as memorials to what could have been. Proxima b extends that lesson outward in scale. It reminds us that habitability is not just local, it is orbital, stellar, magnetic. A planet can be in the habitable zone and still be doomed before life even begins. Proxima b's star is its greatest danger. Every flare that strips air, every burst of ultraviolet that fractures water, is a reminder of cosmic indifference. We live around a sun that burns gently, supported by a rare combination of mass and stability. If Sol had been a little more violent, our oceans could have boiled away before Earth finished cooling. If its activity had been unstable for a few thousand years longer, evolution might never have gotten the chance to build anything more complex than bacteria. If even that. Earth's future is hidden in the physics of its star. Our sun will not flare like Proxima, but it will age, it will expand, it will brighten. Over millions of years, the habitable zone will drift outward, oceans will evaporate, climate feedback loops will accelerate and stabilize at extremes. Eventually, Earth will become a world of steam, then dust, then nothing. The difference between us and Proxima b is not outcome, it is timeline. That is why the silence from Proxima b carries weight. If a world so close to us cannot support life now, what does that say about the cosmic odds? We look outward searching for neighbors, but perhaps we keep finding graves instead. Worlds where life almost happened, where the chemistry was right and the orbit was precise, but the star refused to cooperate. It is easy to imagine we are common. The reality may be that we are rare, not because planets are scarce, but because stable stars are. The warning is simple. We cannot take our equilibrium for granted. Climate is not something Earth has. It is something Earth negotiates every second with a star that barely notices us. Magnetic fields weaken. Atmospheric erosion accelerates. Human civilization acts as if it stands outside these forces when it is seated directly inside them. Proxima b is a demonstration of fragility. It reminds us that intelligent life does not appear because the universe encourages it. It appears in spite of the universe. If we ever reach Proxima b, we might not find aliens, oceans, or cities. We may find an empty world, a mirror held up to our future, telling us what happens when a planet loses the quiet balance that made life possible. The planet is not a promise, it is a question. The universe asks whether life can endure near a star that burns quietly for trillions of years, but screams in flares strong enough to erase oceans in a heartbeat. When astronomers first detected Proxima b in 2016, the headlines were ecstatic. An Earth-sized world orbiting the nearest star to our own. People imagined oceans, continents, alien sunsets. They spoke of interstellar journeys and new homes waiting in cosmic neighborhoods just 4 light-years away. But as the details sharpened, optimism fractured into uncertainty. The more we learned, the more Proxima b became a riddle instead of a refuge. It is a planet trapped between extremes. Its day side is seared by unending starlight, its night side frozen under a sky that never brightens. Its star is both eternal and unstable, an ancient ember that lashes out unpredictably. Where Earth has seasons, Proxima b has hemispheres. Where Earth has calm skies, Proxima b has cosmic storms. It is a world that forces us to reconsider the very meaning of habitability. Earth-like becomes a misleading phrase. Size does not equal sanctuary. What Proxima b represents most clearly is the razor-thin boundary on which life balances. We like to think of evolution as heroic, life crawling out of oceans, discovering fire, inventing language. But life is not heroic. It is opportunistic. It blooms where conditions allow it and vanishes when those conditions collapse. Proxima b is a reminder that the cosmos is not rooting for us. It is not constructing ecosystems with care. It is a machine of physics. And in the machinery of red dwarfs, planets are no more than collateral. For some scientists, the planet is a laboratory of possibilities. If life exists there, it must be resilient beyond anything on Earth. It would not be shaped by sunlight but by shadow. It might feed on heat gradients, or minerals, or faint infrared rays. It might live beneath continents, or under oceans sealed in ice. If evolution can survive Proxima b, then the definition of habitable worlds explodes outward. Life may not only endure, it may thrive in places that look hopeless to us. For others, the planet is a warning. It shows how fragile biospheres are, how quickly oceans can disappear, how violently stars can change the fate of worlds. Humanity tends to view the cosmos through a lens of exploration, colonization, destiny. But Proxima b whispers a sobering alternative. The universe is full of failures, dead starts, unfinished attempts, worlds that almost lived. Ultimately, Proxima b forces us to look inward as much as outward. We search the stars for comfort, for reassurance that Earth is common and life inevitable. But the closest Earth-sized planet to our Sun may be uninhabitable, scarred, silent, not a cradle, but a tomb. A reminder that luck, not inevitability, gave us oceans, air, blue skies, forests, and the ability to wonder. Perhaps that is the meaning. Proxima b does not tell us what we will become. It tells us how easily we could have been nothing at all. And now, as our journey through the red twilight of Proxima b draws to a close, let your mind drift back across the void. A world that orbits every 11 days, scorched on one side and frozen on the other, continues its silent dance beneath a restless star. We explored its oceans that may be gone, its ice that may be miles thick, its underground shelters where life, if it ever found a foothold, might still hide in the dark. We considered a future where human settlements stretch like a ribbon around its twilight belt, clinging to the thin strip of calm between heat and frost. What Proxima b offers us is not comfort, but perspective. It reminds us that habitable worlds are not guaranteed, and that the calm of Earth is a rare cosmic arrangement, one we must never take for granted. When we look up at the night sky, we do not see promises. We see questions. What survives? What endures? What fades without leaving a trace? If life taught anything on Proxima b, it was how to survive under a star that refuses to be gentle. If we ever stand there, gazing at a red sun that never sets, we will carry with us the memory of oceans that listened to moonlight, forests that moved with wind, and skies that changed with morning. We will bring Earth with us, not in soil or water, but in gratitude. So breathe deeply. Let your thoughts quiet. The universe is vast, ancient, and complex, and we are lucky to exist within it, on a world that still shelters us. Rest now. Let the stars keep watch, and drift into sleep, knowing that even in the immense darkness between suns, you are part of something extraordinary.